Hello everyone. So, let us continue our discussion. We are in week 5 and this is our lecture 2. Today we are going to solve some example, right? But before that, let us quickly review what we have done. So, earlier we have studied 3D strain analysis. And we defined strain displacement matrix. If you recall, strain displacement matrix. So, first let us define the displacement field. So, we have considered 3 components of displacement field. What are those 3 components? Ux, Uy and Uz. All of them are function of x, y, z, right. So, they are function of x, y, z. Now, if that is the case, then we defined first displacement gradient matrix. And this displacement gradient matrix is given by its elements, which are Ux differentiated with respect to x, then Uy differentiated with respect to x, then Uz differentiated with respect to x. So, that is the first column. Second column, Ux differentiated with respect to y, then Uy differentiated with respect to y, and then Uz differentiated with respect to y. And the third column is Ux differentiated with respect to z, Uy differentiated with respect to z, and then the last one Uz differentiated with respect to z. So, that is the displacement gradient matrix. Then we defined a line whose changed length we can express in terms of its initial length plus epsilon pq, right. This is the linear variation of strain. In fact, we developed higher order effect, but we considered only linear part, and because in our course we will consider only linear part, and for that the different strain components also we defined. So, we had 3 normal strains. So, the first one is Ux with respect to x, then Uy with respect to y, and the third one is Uz with respect to z. Then shear strengths gamma xy, gamma yz and gamma zx. These are very easy to write. So, first one will be Uy with respect to x plus differential of Ux with respect to y. Similarly, Uz differentiated with respect to y plus Uy differentiated with respect to z, and the last one Ux differentiated with respect to z plus Uz differentiated with respect to x. And in fact, here it is very easy to prove that gamma xy is equal to gamma yx. Similarly, for the remaining 2 directions also we can prove the same thing. Then we also derived the expression of epsilon pq, right. What is that? If you recall, epsilon xx nx square plus epsilon yy ny square plus epsilon zz nz square. plus gamma xy nx ny plus gamma yz ny nz plus gamma xz nx nz. In fact, also we defined epsilon xy and gamma xy, right. If you recall, these are the two quantities and their interrelation also we defined. Other way we can express our strain component for a line segment which is defined by PQ. Okay. Now, let us solve some example. Okay. So, our first example today is where we are given a displacement field. So, example 1, u is equal to x square plus y I plus 3 plus z j plus x square plus twice y k. The question is, first evaluate displacement gradient matrix at a point two, 3, 1. Second part, evaluate the linear strain components at the same point. So, what we do? We first identify u x, which is x square plus y, then u y, which is 3 plus z, and then u z, which is x square plus twice y, right. So, we can differentiate u x with respect to x, which is twice x, then u x differentiated with respect to y, which is 1, and then u x differentiated with respect to z, which is 0, right. Then u y differentiated with respect to x, which is 0, u y differentiated with respect to y, which is again 0, then u y differentiated with respect to z, and that is 1. U y with respect to z, yeah, it is 1. Then u z with respect to x, that is twice x, u z with respect to y, which is 2, and the last quantity u z with respect to z, which is 0. So, the first part, displacement gradient matrix, is given by first term 2 times x, we have to evaluate at the point 2, 3, 1. So, it is twice x, 1, 0, and then 0, 0, 1, and then twice x, 2, 0, right. So, if we evaluate at that point 2, 3, 1, first element is 4, 0, 4, then 1, 0, 2, and then 0, 1, 0. So, we get the first answer. Second question, we have to find out epsilon xx, which is this quantity. So, 2x, that is at 0.231 it is 4, right. Similarly, epsilon yy, which is here and it is 0, epsilon zz, which is here, again it is 0. Then we have gamma xy, that expression we have already derived here, right. So, uyx, so this one plus this one, right. So, we have 0 plus 1, which is equal to 1, then gamma yz. So, we have this one 2 plus this one, right. So, 2 plus 1, which is 3, and the last one zx is uz with respect to x, which is here twice x plus here 0, right. So, 0 plus twice x at the point 231 it is 4. Okay. So, now we have all the components of strain. So, we have 4 0 0 and then we have 1 yz is 3 and then xz or zx is 4. So, that solves the problem, right. Remember, we have linear variation of strains here. So, we have axial strain and shear strain, right, and that we evaluate at a point 231. So, that is the first problem. Let us take a different problem. Example 2. The problem says derive the volumetric strain of a parallel pipe defined by PQRS. I will just draw the figure in a minute. So, what we have to find out? Volumetric strain. So, for that we have to find out initial volume and final volume, and from that too we can easily quantify the volumetric strain. So, let us consider the figure first. So, we have XYZ axis and then we have 3D volume defined by PQ, then R, and so this is S. And the size of this 3D volume is delta x, delta y, delta z, right. Okay. Now, after deformation it shifts somewhere here. So, this is my P prime and then we have the other edges. So, it deforms in 3D. So, this is Q prime, S prime, R prime. Okay. So, recall we have already studied this expression that we are going to use in this problem. So, delta S prime is equal to delta S times 1 plus epsilon P q. So, if you consider this edge P q, after deformation this is the length and delta S is the initial length, right. Likewise, we can actually write down the complete elongation of other edges like PR, PS following this mathematical model. If we do that, so we have P prime, Q prime, then P prime, R prime, and then P prime, S prime, and we have x axis, then y axis and z axis. So, along x axis we have the elongation 1 plus differential of u x with respect to x times delta x. So, for this P prime R prime, we have u x differentiated with respect to x times, differentiated with respect to y times delta y. Then for P prime S prime, it is u x differentiated with respect to z times delta z. Likewise, we can populate all other components. Right. Now, what we have to find out? We have to find out initial and final volume. If we do that, we can easily evaluate the volumetric strain. So, V initial is very simple, it is delta x times delta y times delta z. V final is also very simple. The moment we define all these elements, it is d times delta x, delta y, delta z. And what is d? d is nothing but the modulus of this element. So, we have 1 plus differential of u x with respect to x, then this one u x with respect to y, and then u x with respect to z. Similarly, let us populate the remaining terms. And if we find out this determinant, of course, we will have 1 plus the linear variations and then we also have higher order variations, which I am not writing, because these elements individually they are very small. Okay. Product of that, because all higher order terms will have square or product of these elements, obviously they will be small. So, here we can neglect all higher order terms, higher order terms. So, if we neglect that, then we are left with this linear variation, and so that is a approximate estimation if we consider the linear variation which is defined here, right. Then what is the final volume? V f n is equal to 1 plus times V initial. Therefore, we have V f n minus V I n divided by V I n, that is the volumetric strain, is and these are nothing but the summation of all axial strains or normal strains. Right. So, we get volumetric strain del V by V is equal to summation of the leading diagonal. So, that is the expression for volumetric strain. Right. Okay. So, let us take a different problem. Third problem. Given Ux, Uy and Uz, where k is a constant, first evaluate the 3D strain field, and the second part is evaluate the strain along Nx equal to Ny equal to Nz is equal to 1 by square root of 3. Okay. So, what we will do? Let us find out epsilon xx, which is uxx differentiated with respect to x. So, we will have ky, right. Similarly, epsilon yy is, if we differentiate this with respect to y, we have kx, and then epsilon zz is the last one differentiated with respect to z. So, we will have twice k times x plus y. Now, we can find out shear strains. So, for this we have uy differentiated with respect to x and then ux differentiated with respect to y. So, uy with respect to x, so we have k times y plus second term is k times x. So, this is k times x plus y. Similarly, gamma yz is so we have twice kz plus 0. Okay. So, this is twice kz. Last component gamma xz is equal to right. Then if we just write down all the elements in the matrix form, so we have ky and then k times x plus y, then twice k z, then kx, k twice k z, and then twice k x plus y. Right. So, that is the first part, and then we have to find out. So, this is first part. Second part is epsilon p q, and for that we know the expression epsilon x x n x square plus epsilon y y n y square plus epsilon z z n z square plus gamma x y n x n y plus gamma yz in y and z plus gamma xz in x and z. And if we put the expression of direction cosines, this is 1 by root 3. So, we can take 1 by 3 common, and then within bracket we have ky plus kx plus twice k x plus y plus gamma xy, it is k times x plus y plus twice kz plus twice kz. And if you look at this expression, we can take this k common first thing, and then we can open this bracket and further simplify. If you do that, we get 4 times k by 3, and within bracket we have x plus y plus z. So, that is the epsilon pq. Okay. So, you have seen how we can use the strain in 3D to solve some problem. So, the moment we start with the displacement field, we can easily find out different components of strain. Of course, we have considered linear variation. You can extend it to higher order variation also, but for the time being in this course we are worried of linear variation only, and then accordingly you can find out the 3D strain field, and then from there you can easily estimate the elongation of a line defined by say PQ. So, what is the strain along a particular direction, which is given by this nx, ny and z, that is the direction cosines. So, we can easily find out, right. Also, if we have a volume, then we can estimate the initial volume, we can estimate the final volume, because once we quantify this epsilon pq, you can see here. So, this epsilon pq, then we can extend that model for all the edges of our 3D volume, and then we can evaluate the final volume, and once we evaluate the final volume, we know initial volume, we can easily estimate the volumetric strain. So, with that, let us close here. As we progress, first we will solve some example for principal strain, and we will also see how to develop some compatibility conditions. That is most important, because once we are given the displacement field ux, uy, uz, we can find out the strain field. That is very easy, straightforward, because we need to basically differentiate the displacement field with respect to x, obviously for linear strain. But if we go for the reverse, that means once we are given this components of strain, and from there if we need to find out the displacement field, that is ux, uy, uz, then we need some additional criteria. Otherwise, if you look at this expression here, look at this expression. So, from this expression, if you integrate, you can get ux, right. At the same time, if you consider this expression, you also have ux here. So, which ux will be the unique solution, that we will study, and for that we have to develop some compatibility conditions. So, that we do in the next class as we progress in this course. If you have any doubt, please drop a mail to us, then we will clear your doubt, or otherwise you can also discuss the problem in our open session. Thank you very much.